But there's good news, which is that our monthly program chair, Thad Gabara, has volunteered to give a presentation today on very short notice. And we thank Thad for being a stand-up guy. We have already introduced Thad as the monthly program chair for September. He has a solid technical background, as you may remember, and experience, as well as the many patents that he happens to have to his name. He is going to draw on his experience back at AT&T in his working life to give us a history and wonders of the 32-bit microprocessor. Thad, the podium and microphone are yours. Please welcome Thad.
Okay, so while we're waiting, I'm going to be talking about semiconductors, and I'd like to see who knows or has heard of a metal oxide semiconductor device. Raise your hand. All right, so there's a lot of people here, good. And then the second question is, who knows or has heard of CMOS, complementary metal oxide semiconductors? Of those people that raised their hands, do you know how it works? All right. So I think we're going to take a look at that, and we'll see how that works out. I'm going to be looking back into the 70s, the late 70s, where AT&T decided to do a microprocessor. And once we get these slides going, and I'm not even on the screen, so let me fix that. Oh, the other thing is we're going to talk about NMOS, PMOS, and CMOS, but we're going to do it in a way of physical structures. So everything will be done as though you're really looking at the physical world. And then hopefully that should help see how these devices made a play within AT&T's microprocessor range. By the way, the yield on this chip was extremely poor. You would process a lot of wafers, not a lot of wafers, but you also do a lot of wafers. But you usually process something like 25 wafers. And there was a case that since the yield is so bad, they were expecting one chip out of all of the wafers. So the yield was so low at one die per lot. We're talking, it's like an unbelievable low yield. The lot came out on one of the times because there were many lots coming out. And we had a summer intern, and he took the lots in this case, and he ran up the stairs, and he tripped, and the whole case went down the stairway. It broke all of the wafers. And once the wafers are broken, you can't test them. It's really garbage. And I don't know what happened to that student. I never saw him again. Well, the microprocessor design at AT&T was a tremendously huge project. It extended all the way from Indian Hill in Chicago to Homedale down in Jersey to Murray Hill here, right in the next town. And there was even some people coming in from Whippany. The goal was to make CMOS reliable. Yeah, and at that time, CMOS was known. It was the first MOS transistor was invented at Bell Labs in 1960 with it's Mohammed Atella and Duan Kong. Excellent. And I guess we're looking. Okay. So I gave you some questions earlier. Let's take a look at the late 70s. The 8-bit microprocessor was ruling the world, and the 8-bit microprocessor was fabricated with NMOS devices. We see here the Intel 8085 and the Zilog Z80. These were very popular chips. They were driving the microprocessor industry. They're beautiful designs. You probably can't tell, but their hand layout, they're just wonderful. And what AT&T decided to do was they wanted to leap ahead and enter into this market. They're competing in the market that's 8 bits. They're going to make it, oh, maybe I can even stand up. They're going to make it a very competitive chip, and they're going to implement 7 initiatives. And one is fabricating the chip in an unproven CMOS. And what we see here is a picture of the Blue Zoo. This is a room that's inside of Bell Labs up on the 4th floor of building 7. And in this room, it was so clean, it had 100 particles per cubic foot. And here they implemented all the designs, built the process, and what they ended up with is the AT&T Bell Labs twin tub CMOS process. If you take a look at 50 and 51, those are the tubs. And within the tubs, you can see the gates of the transistors are 60 and 61. And so there's special, the N-channel transistors are on the left in the P-tub, and the P-channel transistors are in the N-tub. And the individual tubs give the ability to do individual adjustments on the transistors, which was a big step forward. And it only required 8 masks, and we'll see what a mask is shortly. 2, they wanted to create a 32-bit architecture. That's a bold leap from going all the way from 8 bits to 32. Next, they wanted to move 32 bits in a single clock cycle. And here we see what's encircled are the I/O interfacing with the world at 32 bits. And inside of the chip, there's a C bus and an A bus, and they were running at 32 bits. They were running 32 bits simultaneously, and this is back in 1979. Lastly, if it's coming from AT&T, it has to support Unix. And I used Nana Banana to get that picture. Isn't it a beautiful picture? And what the name of the project is, it's Bellmac 32, just as on that chip. And let's take a look at some of the characteristics of the Bellmac 32 microprocessor. Mentioned that it's a twin tub technology. We saw that before. And we see some numbers, 3.5, 2.5, 1.75 microns. This is 10 to the minus 6 meters. And these numbers are decreasing because everybody is progressing on reducing the channel length. So for instance, in the 2.5 micron CMOS, the channel length was 2.5 microns. You could fit 3 of these transistors side by side across the diameter of a human hair. The chip was built on a piece of silicon that was 1 centimeter by 1 centimeter. It had 150,000 transistors. At the time, that was a huge number. Today, it's a pretty small number. It was clocked at 2 megahertz. Today, we're dealing in gigahertz, 1,000 times higher. Power dissipation was low, only a watt, and it uses something called domino logic. That's a circuit technique to speed up the CMOS devices. And the Bellmac 32 was released in 1980, and it was the first 32-bit microprocessor out there. You know, you might find controversy, but you can look back in the records, and AT&T has the first CMOS microprocessor. And this is a picture of the die. And you can see around the perimeter, there's a different looking environment, and that's where you bond to the chip. And inside of that outer perimeter is the circuits, all of the circuits, and they're all interconnected. So here's basically 150,000, what 150,000 transistors look like. And we're talking about CMOS. It is CMOS. And if we take, and as I mentioned, we talked about CMOS, NMOS, And now I'm going to say PMOS. So the N stands for negative, the P stands for positive, and the C stands for complementary. And we'll see how they all fit together shortly. But the common root on all of them is MOS, and a lot of people raised their hands here today knowing what that is. And it's the metal oxide semiconductor. We know what metal is, we know what oxide is, but what is semiconductor? So a semiconductor is quite a unique device. Here's a slab of semiconductor. Its unique quality is that it is able to change its electrical characteristics through external forces. So one of the things that we do want to change is its electrical conductivity, and it's a variable. And it's going to be changed by switches. And you're going to take this piece of semiconductor and you're going to make it a insulator like glass. With a flick of a switch, you're going to go all the way to the other end to make it conductive like metal. All with a flick of a switch. Now, when we apply the electric fields to achieve this control, you think you're going to have a piece of metal. And you're somehow going to connect to it? No. If you connect that metal to the semiconductor, you got a Schottky diode or a diode structure. So that was already invented. That's not what we're looking for. We're looking for a piece of metal that comes close to the semiconductor, but not touching it. And so when I say we apply a voltage across a distance, we're applying it across that distance that is close to the surface. This semiconductor is actually silicon. And if you know anything about the oxide of silicon, you'll know that it's silicon dioxide. And silicon dioxide is found on the beaches. It's found everywhere. So here you have silicon. Its natural oxide is silicon dioxide. We're going to leverage it. So what are we going to do? We're going to grow an oxide on this silicon. And how do we grow that oxide? We're going to stick it into an oven. And we put our wafers in, we throw it into an oven. And now going into this oven, it's regulated at plus or minus 1 degree centigrade. It's heating this thing up to 1,000 degrees centigrade. The high energy allows the oxygen to come in. It starts building a film, and then you're done. And when you can pull it out, the one thing is, everything is well controlled. You know how long you kept it in there. You know the temperature. You know how well you controlled it. Therefore, your thickness, it's going to be a carefully controlled oxide thickness. That's exactly what you want on this silicon. Because if you're going to make this product and you're going to sell it, you have to repeat what you're producing. That oxide level must be well controlled. And we can do that with this technique of heating it up. Now we deposit the metal on it. And so this is the one question that I asked. What is a metal oxide semiconductor? That's what it looks like. But we're looking at it in a way kind of abstract. Let's look at it 3D. So this is what you're really looking at, is this structure. And the top part is metal. It used to be, it's now poly, by the way. It's no longer metal, but it doesn't matter. So we have metal, oxide, semiconductor. And so that's a pretty good name. I guess the name follows what the structure looks like. So let's go back to 2D. Now that we have this structure, then we want to come up with some rules that we want to follow. Like, how many charges are there? And there's two. There's electrons. Electrons have a negative charge. Holes, which are the absence of electrons, have a positive charge. And we're going to use a negative charge and a positive charge. And then there's another rule. You probably learned this in grammar school, that opposites attract and like repel. So we have to remember these two rules. That's all you need to know. And now we're going to apply a voltage. We're going to put a voltage on the metal, and we're going to put a voltage on the semiconductor. On the metal, I have the switch to a 1. The semiconductor is a switch to a 0. 1 is bigger than 0, yeah, and therefore 1 is more positive than 0. Since 1 is more positive, what happens once you do this? You create an electrons in the channel. You can see the electrons forming near the surface, but that happened because the positive charges came onto the metal. Remember, positive attracts opposites. It's pulling the electrons out of that p-type semiconductor. That p-type means it's the majority carriers are holes, but we are using electrons in this channel. And the way we get that is we invert the semiconductor. And I'm not going to talk about that anymore. All I'm going to say is that this voltage applied to here generates an electron layer that's close to the silicon. That electron layer is like metal. If I can put contacts on the left and contacts on the right, I can connect to that metal. And by flicking the switch, it goes to be an insulator like glass. What a fantastic device. And this is in all of your pockets. And this is the beginnings of basically, we want to use this enhanced connectivity. So I got ahead of myself. And so how are we going to do that? Oh, before I do that, let's take a look at that path going from 1 through the semiconductor to the 0. You could see that the voltage of the 1 and 0 is across the oxide. And that voltage causes that conductivity channel. But let's utilize this capability. What we want to do is slap on some contacts to the side. The contacts that we're slapping on are going to help provide the electrons and drain the electrons. And so here we have the source drain contacts, which are the same as the electrons. So the source and drain is N-type. The semiconductor type is opposite to what the source and drain are. So it's P-type in the middle, and you get your electrons from there as minority carriers. And so what you're looking at right now is an NMOS device. And if we look at the symbol of the NMOS device, if you compare the G with the gate, that oxide with that gap up beside the G, and then the D and S, and the square box that's in there represents the semiconductor. So that's a pretty good model of a representation of what the MOS device is, the NMOS device is. So we've taken a look at changing the gate voltage, and we developed that negative charge, but we haven't utilized it yet. So let's turn the switch and apply a potential across this and see what happens. And if we do that and we enable that switch, then the electrons come from the source. And look at that. They called it the source. What a beautiful name. It's the source of where the electrons come from. And then they travel across the length of that semiconductor. And where do they end up? They go down the drain. They go to the drain. All right, so this is a beautiful name. You have a source and a drain, and it sort of defines how this device works. But now that it's pushing this current, it's dissipating power, it's doing something, I want to shut it off. And the way I'm going to shut this off is I'm going to put a voltage on the gate. And if I do that, everything goes away. And so there's now no longer a sheet of metal there. It's now a piece of glass. So with one flick of a switch, you go from metal to glass. So now, if we take a look at the path, to make sure that the voltage across the gate is zero, the zero is applied to the metal. We go through the oxide and we go to the zero voltage. There is zero voltage across this oxide. There cannot be a channel. So let's go back to what we had. And as I pointed out, it's acting as an insulator right now. But let's go back to turn it into a piece of metal. And now we want to optimize this channel for speed. Because the channel length, there's something called the transit time. And if you throw something into the source, and then it goes through the length of the channel and it makes its way to the drain, the longer that is, the longer you have to wait. You're putting information in at the source, and that information doesn't get to the drain until it gets there. So there's a delay. If that channel length is really long, guess what? It's going to take you a while to get that signal out. So what you want to do is, since channel length dominates this, you want to reduce the channel length. And if you can reduce the channel length, you get speed. So let's reduce it. So there's our reduced channel. We saw earlier, I showed you those numbers of 3.5, 2.5. We're reducing in size. This is the way industry is going. Now, what do you get out of this? You can see the channel length has been reduced, and you get increased transistor performance, improved device density. If you decrease the size of the transistor by X, the area goes down by X squared. That means you're going to fit a lot of transistors into there. And also, because the transistors are smaller, there's less capacitors to move around. You get lower power consumption. This is one of the primary reasons why AT&T chose CMOS over NMOS, which was a power dissipating technology. But the CMOS wasn't ready for very large scale integration. So AT&T had to drive that. So here's what happened after, if we look at the top left, it's about 1.5 microns. And we're looking basically at the year from 1980 to now. And we're looking at that technology number that I was talking about. I showed you the 2.5. Well, as time went on, we went down to 180 microns. And today we're at 1 nanometer, or getting close to 1 nanometer. It's like 1,000-time reduction. So more transistors can get packed into a given area. So let's take a look at that curve. This is the RUP curve. It's 50 years of microprocessor evaluations. The orange curve is in the transistor count. The green curve is frequency of operation of the chip. The red curve is power. So let's see where our microprocessor stands, right about there. So we were running at 2 megahertz, pretty slow, 150,000 transistors, at the time, a phenomenal number, 1 watt and 3.5 microns. Now you wonder, biological. How big is 3.5 microns? E. coli, bacteria, and pollen is about the size of that. So back in the 80s, we were designing transistors with lengths that had this kind of a size. But it's today now. And we know that Apple has a microprocessor. It's called M3. It runs at 4 gigahertz. That's quite an improvement. And by the way, it's sitting where that arrow is, roughly. Wait, is that number wrong? That says 184 billion. Yeah, that's billion. There's 184 billion transistors in there. It dissipates 270 watts. You can probably take one of these chips from Apple, and if you're buying a new stove, put a couple of them on the counter, and anytime you're running your design, you can fry an egg. And it's at 3 nanometers. Now, 3 nanometers. What kind of living thing is 3 nanometers? Well, I had probably DNA and stuff, but stack 6 water molecules together. That's the size of that channel length. And that's where they are today. That's just remarkable. So here's the improvements between the Bellmac and Apple's chip. The frequency went up 2,000 times. The transistor count, it went up 1.2 million times. The power went up 270 times. And the process length, we decreased it 1,100 times. So where we're standing at today, and you know that TSMC is trying to come here to build chips, and they found out it's very difficult because you're going into this domain. It's completely different than when I started in the 80s. Now, one more thing I want to do is create the PMOS. Now, I have an NMOS on the left. And what the rule is, you take an NMOS and you can duplicate it, which I'll do on the right. So the right is exactly the same as the left, but I'm going to put some criteria on this. I'm going to flip all the semiconductor types. So if we look, I wonder if I could do this. Oh, yeah, I can. All right, so if we look here, this source is N-type, and this source is P-type. They're opposite. And notice that I also flipped it. Remember, we were talking about charges. You can only have plus and minus. Well, you can only have a P, and you can only have an N. Well, if you take the P and you flip it, I'm also flipping its structure like that. So I flipped the sources and drains. And here, if we take the P-type in the semiconductor, I made it an N-type. The next thing you got to do is change your voltages. And so here I have a 1, I go to a 0. Here I have a 0 at the source. I go to this source and I put it to a 1. And once I do that, and I have this structure, which is identically in shape, but different components, the opposite component in the plate, you now have a PMOS. And there's the symbol for the PMOS with a bubble at the gate. That means a 0 makes it active. And when you put a 0 on this gate, you get holes in the semiconductor. Those holes make the metal. So now you have 2 devices. They're opposites of each other, and they behave identical when you take a look at the voltage and waveforms that are placed across them. And so because they're so opposite, they're complementary to each other. So are you getting an idea where CMOS might be going? So now what we do is we want to put the NMOS together to make CMOS. So this is that same thing that I shown you earlier. And the first thing we want to do is connect the gate to the gate. The next thing we want to do is connect the drain to the drain. And you can see why I flipped it. All right. Now, what I want to do next is apply an input to the metal gate. And I'm going to set the input to a 1. And if I do that, you'll see that the output is a 0. And if we work it through, we'll see that with a 1 at the gate of the metal, only the N channel is on, the P channel is off. What a beautiful circuit technology. You're not dissipating any power. Your output is a 0. There's no current flowing. Let's flip it. Now watch the charge in the channel on the left and what happens on the right. Because I flipped it, everything changes. Don't forget, this is complementary. They're opposite. So when I put a 0 in on the input, the output goes to a 1. If I go back to a 1, the output goes to a 0. Well, you know what this is? This is an inverter. And this inverter is a beautiful design. It consumes power only when you switch. So when you go from a high to a low, you use power. But once you're down at the low level, it's for free. You just sit there. There's no power. And so this is sort of reinforcing why AT&T picked this for the microprocessor. And I didn't show you what the NMOS NMOS circuit looks like. NMOS is built, an NMOS microprocessor is built only out of NMOS. And so it has you can make a network out of it with using the N channels, but the connection to the power supply is through a resistor. So that means anytime I put a 1 on A, that turns into a sheet of metal. That sheet of metal shorts out R to 0. And you get a humongous current just to drive out a 0. Remember, CMOS in this same situation had no current. And this is running current for at least half the time, because when it goes the other way, then you save for NMOS. But when you go to the 0, you pay in power. You get great speed with NMOS, and that's why everybody was there. But you paid for it with power. And AT&T knew if you're going to go to 32 bits and higher, you can't use this kind of power capability and put that onto your design. You need to have no power once you switch. Now, not all is nice, because there's a consequence of going to CMOS. And that's that your transistor count doubles. But this gate, no matter how you switch it, once it's done, there is no current in it. It's done. It's going to give you the voltage. There's no power dissipation. Now, in the early days, when we were doing this microprocessor, verification tools were not there. You had to do everything by hand. So what you would have is your design would be made, but you're not sure, so you print it out, you tape it together, you find the biggest area in the building at AT&T, you lay this thing out, and you go with pencils and with colored pencils and mark it out. This is automation at its best. Now, you might want to correct errors, because fortunately, they invented the eraser. And now, when you're designing your microprocessor, you realize, oh, I made a mistake. Let's correct it. Now, once you've made this piece of paper, you notice it's got a structure that kind of looks regular. Well, the next thing you do is you give it to the guy who takes a digitized pen and takes that information and puts it into the computer. What that develops into is something of a layout that is very regular and grid-like, and it's called gate matrix. That was one of the first CAD tools that were developed for the layout of integrated circuits and to verify it as well. Now, when you get all of that done, you're looking at the layout, you might want to make some changes And now you look at the layout on the screen and you physically go in there to make modifications. And that's called a symbolic layout. And that's what the transistors would look like if you could see them through a microscope. But this is actually on a computer. The next thing is, once you have all of those blocks put together, you make super blocks. Because you're not going to build the whole chip together. You're going to build it in pieces because you're going to assemble teams to work on different sections. So these different sections build different components, and they got different block sizes and everything. So they put it together, and then they run it to the guy who does automatic wiring at the LTX level, at the global level. So you connect all of those blocks together with wire. And you see that I'm gonna show you a picture of the Bellmac. If you look at the top, there's rectangular regions. At the bottom, there's a giant rectangular region. And in between the two, there's wires. Remember that. We can verify the chip building in with a management unit, a memory management unit. And we put the chips onto this platform, and note that it has pins. So this sticks into a board. And then that board sticks into a rack. And that rack is probably 5-6 foot high. And then there's multiple racks. And then you all connect everything together to communicate between these various systems. So the early results, the manufacturing yield, I mentioned 1 good die per wafer, and we probably lost one summer student with that. Work pursued to build these CAD systems. Work was a big effort to do that. The 150,000 transistors stressed all the tools. Don't forget, memory used to be expensive at one time. Well, it still is today. It's relatively speaking. Creating new circuit designs. And today, 99.99, maybe 999% of all the chips in the world are CMOS. The ruling person is TSMC in Taiwan. And as you know, we're trying to get that back here. And we used to be the source of all of that. And bringing that, think about that transistor. It's a few water molecules wide. You have to bring that capability back here to have that kind of control. So let's take a look at silicon processing. I want to see how much time I have. All right. And we're going to look at packaging, silicon processing and packaging of the Bellmac 32. We start out with an ingot on the left, and this is like silicon. You pull it out of a melt real slow, and you can build these crystals. And once you have them, you slice them up, and you get silicon wafers. And now that you have that, we drop a photoresist. Remember, we took that wafer, we threw it in the oven. It came back with an oxide on it. The next thing we're going to do is we're going to put photoresist on, spin it off, we're going to heat it up, and we're going to make a mask. So here's what a mask might look like. And then how do we use this mask with the photoresist? Well, we take an energy source, we go through a condenser lens, we go through the mask. It's also called a reticle. Then we go through a reduction lens, and then we transfer the pattern that's on the mask onto the section of the wafer that I'm going to have the chip. And once I process that and use light to that photoresist, some of it gets hardened, some of it gets weakened, and the one that doesn't get exposed could stay the same. And then you can go through an acid bath and remove it. But the next thing that you do here is you do step and repeat. And you move to the next location on the wafer. And here's one of the processed wafers. You can see what the step and repeat is. It's 2 centimeters. So you basically make an image, and then you go down to the next one and the next one. You repeat this for all of the 8 layers. So look at the number of steps. Bellmac 32, I told you it was 8 masks. But, you know, that's not the only thing you got to do is 8 things. Because at each step, there's sub-steps. You have to spin the resist. You have to bake it. You have to expose it. You got to develop it. You got to wash it. You got to metallize it. So at each one of these steps, there's a number of sub-steps. So approximately 50 to 70 processing steps were required for the Bellmac 32. Remember that, and that was a big deal. You know, a low number of masks means you have less problem on the number of steps. Today, they use 400 masks. Imagine that. And they do it with that accuracy of 6 water molecules. On all of these layers, on all of the 400 masks, everything is perfect. But that's 400 masks. How many steps are there? 2,000 to 3,000 steps. What a complicated process. Imagine you woke up and today you're in charge of building that chip with 3,000 steps, and you have to do it every step perfect. You make a mistake on any step, throw it out. Now, once you have your chip on the wafer, you got to figure out which chips on the wafer are good. You're not going to cut the wafer apart and get the chips and test them because that's a waste of time. The chips are all together nicely patterned on this wafer. So we're going to test it while it's in the wafer form. And what we see here are tungsten probes that are looking down on the chip, and the mechanism is coming up to make contact with those probes. And those probes push in vectors, read out the vectors. They're doing all the tests necessary to see if that chip is working. And look at how long it takes. That one's taking a little longer, so that must have been a good chip. All right, that one's probably a good chip. All right, but this is what you have to do, and then you mark it, and it gets marked. And remember, I told you, when we looked at that LTX, the global routing, look on the top, you can see sort of blocks. And on the bottom, there's one big block. And look in between. That's where that global wiring was done using that LTX machine. Now I'm going to switch gears and go into a cross-sectional view of what the semiconductor would look like. You take a chip, you break it in half, look at the side. And what you'll find is that there's many layers of metallization. So you can connect all on the chip to different places going up to a metal level like a highway. Another level up, there's a different highway. Another level up, there's another highway. And at the top, you can also put on solder bumps onto the chip. And that's a tremendous advantage. I'm going to show you what kind of advantage solder bumps are. Now, I've eaten away that oxide. And this is from IBM 20 years ago. When I first saw this, I said, what an amazing piece of architecture. That thing looks so beautiful. And so they've eaten away all of the oxide, and the only thing standing is the metal and how the metal connects. Isn't that a beautiful structure? And then you have Applied Materials. They're the ones who make all the processing equipment, and they're looking at metallization levels, something like that. That's going to be going onto your chip. So not only do you have transistors that are 3 water molecules across, you're going to have like a highway built up over your chip. So you can connect anything to anything. Now here is the Bellmac 32, and it's packaged. And if you look from the chip to the outside of the package, there's little tiny wires. Those are bonding wires. And this is the way that they're put on. The diameter of that wire is 1/3 the diameter of hair. And it goes all around and it connects the, remember I told you on the outer periphery of the microprocessor, we had that band. And this is where those wires are going. And they're allowing the package to communicate with the chip through the wire. But let's compare wire bound and flip chip. Flip chip is where you have the solder bumps that I mentioned earlier. Here, the chip on the left, you could see that it has the bonding pinpoints, and that's where those wires were going. And then you put the chip on the carrier and you bond it up. You could only get to the perimeter of the chip. That's a limited number of I/O. And so if you can somehow increase the number of ways of getting into the chip, that would be tremendous. And the way you do that is you put those solder bumps onto the chip and you form them up at that top highway level, the most highest highway level that you have. And once you have those solder bumps on there, you flip it. And that's why this is called flip chip. I used to work in this field with Thad. And you would come down, bring it onto the carrier, throw it through the oven would melt it. You've got a beautiful connection. Here's a picture of what the solder bumps might look like. Although it says 55 mm for millimeter, that's an error in the text. They corrected it. It's really micrometers. All right, so you can actually have these bumps on the chip, and what a beautiful way to make connections. It's the advantage. I mean, how good is this advantage? Well, here I'm comparing bonding wires versus the micro bumps. I'm looking at the dimension of the pad that you bond to with the wire, or the solder is on it. And I'm looking at the wire micro bump diameter, the location of where you can put them, number of I/O that you have, and its inductance. Inductance is something you don't want. It's a thing in the circuit that kind of gets at you, you know, and once you put current in it, it jumps around. It's like a lion. You got to walk by it real carefully and slowly. Don't go fast, because if you do, he'll wake up. So that's the problem with inductance. It's slow. If you want to go fast, inductance is a problem. If we look at the bonding wires at the top row, they're the same. The next row, the diameter, the same. With the numbers we've been working with, those are the same. If you look at the location, in one, it's only on the periphery. The other one is over the whole area. So one is linear, the other one's x squared. If you look at the number of I/O, you can get up to 400. In flip chip, 10 to 20,000, 25 to 50 times better. And inductance, you don't have this long wire. You shrunk it to a solder piece, and you've got 1/10 the inductance. That's a big benefit. Here's a package of a packaged Bellmac 32 in a package. He should have washed his hands. Here it is sealed in a hermetically sealed package. Again, I'm showing you that Bellmac with the memory management unit. And again, this is like a module. You plug this in. And here's a description of the several chips AT&T did. And you can see the progression in the reduction in the channel length, the increase in frequency, and the increase in transistor count. And you can see our CAD tools at the beginning, colored pencils. Wow, I'm surprised. It's only a half an hour. All right, anyway, that's good. Hopefully you got a little bit of information on how an MOS device, what it is, how a NMOS device operates and a PMOS device operates. But AT&T played a pivotal role in advancing microprocessors. They adapted the CMOS technology. CMOS technology is used everywhere now. And the innovations that happened here laid the groundwork for many advances that we see. So here are some of the reference that I've used. And here's some more. The last three are really good. There's a YouTube channel that has all sorts of AT&T stuff on it. And that's it. Questions?
So, quick question.
Okay.
Hopefully a quick question. My impression is that designing the intellectual architecture may have been secondary to all of the physical things that needed to be done, all of the processes that needed to be discovered in order to come up with this Bellmac 32. Do I have the right picture?
Yeah, I would agree with that. You're basically going into this project with an uncertain surety that you're going to be able to complete it, because CMOS at that time never was able to handle VLSI chips. VLSI at that time was hundreds of thousands of transistors. That's it. And so that was a big move forward, because maybe that wouldn't have worked. And you're right, probably the architecture would be one of the lower ones, but it was still up there because nobody was doing it in 32-bit at the time.
Thad, thanks for a great talk. I really enjoyed it, and I understand a lot more about these things. I can still remember going from the 8 chip to the 32 chip, how excited I was to get one of the 32 chip computers. So I have an observation first. I still remember going to one of the PC shows in New York, and IBM was handing out memory chips, 1 megabyte. And they were maybe the size of the thumb, and they were in plastic. And I remember I thought I was really getting something. And I talked to the guy, and he says, "We've got millions of these. They're all failures." So,
AT&T took advantage of DRAMs. When you produce the DRAMs, which are the kinds of things that you're talking about, and they're very small transistors, so you could fit a lot of them onto the surface of the silicon. But once you run the test and you come down with those probes, you push the vectors in, you come back up, and it says the memory at location 20 and at 650 is bad. And so you would think they're going to throw that chip away. Not AT&T. They said, we know where the bad chip is. We're going to put it into our phones, the phone answering machines. And even if it loses a bit, who's going to tell on the phone? So they took all of the bad chips that failed, and they reused them. So you're not going to throw them away. The expenses of building these things are humongous. So you're going to figure out a way. I mean, take a look at who's the head of Amazon? Bezos. You know, Bezos, he started his business, and in order to do that, he had to make a huge cloud up there to handle all of his interactions. And in particular, for Christmas, that network had to be huge. Christmas goes, there's an empty network. It's not doing anything. So this is a problem, right? So Bezos goes to his people and say, if you don't come back with me with an idea of how we're going to use this network in those, you're going to get fired. So they came up with cloud. Now you go on the cloud, and any time that it's not being used, it's there for you to use.
I guess my question that I had is, how do you stay sane when you're doing this?
Oh, yeah. I wish I should have bought it. But in the times of Allentown, when I used to work in Allentown in microelectronics, that's true. You know, the problem with these designs is that when you work your butt off and you put all that stuff together and you send it to processing to get it made, you wait 3 months. And now for 3 months, your palms are sweaty, your heels are sweaty. You go, did I do that? Did I do that? And you don't know for 3 months. It's horrible. I love software. You know, you make a change, no, doesn't work. Fix it. So the software is quite nice. It's quick. This hardware stuff, you know, a 3-month delay is terrible.
Thad, thank you. Every time I've heard you present, it's always been outstanding.
Thank you.
My question is, when the 32-bit processor was developed, what were its first uses? Was it just internal in AT&T, or where did it go at that point?
Yeah, the very first use, it was really targeted. You mentioned that we were working with Indian Hill in Chicago. Indian Hill in Chicago does all of the switching. So they have like a 3B switching system over there, and they wanted a microprocessor to design everything. So effectively eliminate the operator that used to see putting the plugs into the switchboard. You know, we want to get rid of all of the people work. And so a lot of that stuff happened at Indian Hill, and it went into the switching system. We love to switch calls.
Thank you. And some of the things about this topic is the magnitude of change and how do we all really value this? I had the good fortune to work with that, excuse me, Admiral Grace Hopper.
Who?
Admiral Grace Hopper.
Oh, yes,
Yeah,
yes.
very fortunate. And she used to take around, when she did her demonstration, she'd hand out little pieces of wire. They said, that's how far electrons travel in a microsecond. So it's like, how big is a nanosecond, I guess it was. And she'd hand out pieces of wire. So you physically figure this out. Now, you look at these big numbers on the transistors. What was it? 1.8 billion was one of them?
180 billion.
180 billion. What was a transistor before these semiconductors? It was a vacuum tube. They imagine 180 billion vacuum tubes. That's what I mean. It just kind of blows your mind. I had a good fortune of working.
Well, you can heat Los Angeles with it.
I had the good fortune of working with the Intel 8008 microprocessors breadboarding them. But I just wanted to say that bit about the magnitude, so you really understand from vacuum tubes to billions and billions of transistors on the thing. So thank you.
All right.
This was really amazing. Thank you very much.
Yeah.
And by the way, Thad told me that you will be tested on the lecture in a few minutes.
At lunch.
No, no kidding. Yeah, a question. Can you say a few words about the financing of the project, government, grants, private funds, and so on?
Okay. Yeah, at the time that we did this, AT&T was a monopoly. And that was a great place to live and work. Everybody, when you have design, there's always a variation in the distribution through the Gaussian curve of when your product comes out, it goes outside the range, and you want to keep that range tight. And so you put design constraints to keep that range tight. Well, at AT&T, everybody put those ranges on their designs. And that means everybody's design had that range on them. And the reason they could do it was because it was a monopoly. We had like money flowing in. It was in the hallways. We used to shovel it. And it was so much money until the breakup. Yeah. The government has a office with AT&T in Sandia, I think. They used to work with Sandia, and AT&T and Sandia used to switch information, but I've never worked in that area.
I had two questions. I really enjoyed that. I'm going to be presenting something that's completely different scale-wise in terms of you guys are working on the micro, making things small. What I get involved with sometimes is getting things bigger. But anyway, that's a story for another day. Anyway, what's the temperature limitation of this big? You always have to have like a fan blowing in the back of the. cabinet to keep things, you know, so is there a temperature limit on these?
Where the chip eventually went, I've never interacted with doing it on the rack, but I'm sure they had fans. The thing was that, remember, I told you we designed to the extreme. So when we did these designs and simulations, we would go down, I think it was to minus 20 degrees, no, minus 50 centigrade, up to, I think it used to be 130 centigrade, if I remember correctly. We designed the chip to work over a very large range. And so everything had to work. So you had to make sure everything worked at those extremes. And that puts a significant amount of work on designing the circuit to make it satisfy all the criteria over that large range. So if you threw it into a heated car, you'd have no problem.
Okay, and second question is, how close are the various elements getting close to the atomic limit in terms of thickness?
Yeah, that's, that's an interesting question because in the 80s, we thought we would never make it down to 1 micron. And so in every technological evolution, there's regions where there seems to be a barrier and somebody says you can't do it. And that's a good thing they say you can't do it, because everybody says, now I'm going to do it. And then so they broke the 1 micron barrier. And now we're down to like the nanometer barrier. And so how far more can we go before everything breaks? I mean, can we just have an element microprocessor? And so how would that work? I don't know, but that's another one of the things that you're not going to be able to go beyond a certain level, but people will figure out how to do something that is in that direction.
Thad, what an amazing presentation. You took us on an adventure. I feel like I was there while you were working on this thing and trying to build it and get it to work and test it and everything else. So it was extremely informative. We have 2 ways of thanking you as a speaker. One is the certificate of appreciation. And there is your certificate of appreciation. And you'll see there's an orchid on the certificate. And at one time in the 1930s, when Old Guard was formed, Summit was an orchid production and distribution capital of at least the Northeast and maybe the country. And the other way we have of thanking you is the Old Guard salute.
And thank you.